Welcome back from the break. Now we'll jump into optimization and optimal control. We'll start by going through different classes of problems that I actually expect that you already have encountered in different optimization courses. And then we will look a little bit at an example problem that we might return to later in the series. With the basis in the traditional optimization, we will look at the main difference between optimization and optimal control. So the standard problem that most optimization courses starts with is linear programming, where you have a linear cost function and you have linear constraints, and in the canonical form you have only positive decision variables. But this is not a problem because you can go from real valued variables to only positive values by putting in temporary variables. So there's no loss of generality to just solve this kind of problem. This problem is guaranteed to be convex, and it's much analyzed whether there exists a solution, whether the solution is unique, and the sensitivity. If we change a parameter, how much will the solution change? And there are many algorithms to solve this kind of problems, and simplex is the most famous algorithm that most students have come in contact with. A short notion about the word programming. Right now we would maybe think that the program is the way we solve the problem, but the original usage of programming, it was the solution that was the program. It was developed during World War II, and you could look at it like this. We have a number of ships, which are the constraints here, and we have a number of items that we would like to load. We make a maximum problem, which is the same as a minimum problem. We could just add a minus sign for all the C parameters. Then a minimum problem becomes a maximum problem. But consider now that X here is cargo loads, and we're interested in knowing how much cargo can we get onto all our ships that we have. And we have one row for each ship, and each ship has its limited space, and each item that you would like to load onto the ship takes up a certain amount of that ship's loading capability. So in this case we are looking at getting as much as possible onto all the ships that we have. And the solution for how to place things on the different ships was called the program. The program was how to place different things on different places. So that's behind the word programming. Then we have nonlinear programming. Then the problem is nonlinear, and we have a general nonlinear function, and we can have a general function for the constraint, and we also can have non-negative if we would like to put it on a canonical form. For convex problems, when F is convex and G here postulates a convex space, then there's a lot of theory available. We have existence, we have uniqueness, we have sensitivity analysis, and there are many fast algorithms that can solve this very efficiently. For non-convex problems, there are some special problems that have solutions, and the main difference between the convex and non-convex problems is that for convex problem we know that a local optimum is also a global optimum. For non-convex problems, a local optimum is no longer necessarily a global optimum. As engineers, if you approach this, you need a methodology to ensure that you get a good solution. For example, you can try with several different initial guesses, or use very advanced global minimization schemes. But when coming to industry, the industry is not always interested in the theoretical optimal solution. They are more often interested in finding a good solution, or a solution that gives a significant improvement compared to what you have right now. And significant improvement need not to be a lot, but it could in some cases be an improvement of 0.5% that the automotive industry is pursuing in terms of getting improvements. Then we're going from linear to nonlinear, and now we have mixed integer and combinatorial optimization, where we start to look at a set of variables here that belong to the integer point, so we cannot have values in between. Thanks to that we have discrete values here, the problem becomes inherently non-convex. And these are generally hard problems to solve. They are much analyzed, and concerning existence and uniqueness and sensitivity too, and there are many types of problems that fit into this area, and many algorithms are available. Now we come to an example problem that is nonlinear and non-convex, but has some interesting properties. We are looking at a vehicle that we are supposed to follow this drive cycle. We know that we need to have 5 gears: gear number 1, gear number 2, gear number 3, gear number 4, and gear number 5. So we know that we need all these 5 gears, but we have not specified what these gear ratios should be. So the gear ratios are free to optimize. So in this case, we will have 5 decision variables, and these 5 decision variables are the gear ratios for the different gears. In this case, we have a countable number of free variables. So there are 5 free variables that we're looking at. The cycle isn't free, the vehicle isn't free, so that is given. But the things that we can change are the gear ratios. And we're just considering the gear ratio as a continuous variable. When we have the model and we have a given set of gear ratios, so we first select all these 5 gear ratios, then as an initial guess we could use, for example, the current design, and when we have the gear ratios we can utilize the model and compute the cost. And then we have the computable set of constraints. That's the model. The model and the cycle are the constraints. The vehicle need to be able to follow the cycle, and we have the model for the vehicle that describes the relations that need to be fulfilled. Then we can formulate the problem where we have the goal to minimize the total fuel consumption over the cycle, where we have the 5 decision variables to optimize over. And we need to fulfill the model and the cycle. So we need to be able to run in this cycle. When this problem is formulated, we can select and apply a solver, and since it's implemented in MATLAB, we can select one of the solvers that we have in MATLAB. Some comments on practical optimization. As I have worked a lot on optimization, I'm giving you my general advice. One important part is finding the right problem formulation. Even though that you think that you have a good idea of what you would like to accomplish, then usually there's a lot of things that you still can do. So finding the right problem formulation, that includes modeling the system, putting up important properties. What is your goal? What are you trying to achieve? And you also add the constraints. What do you want to avoid? Is there something that you don't want to happen? When you have formulated the problem, you find and use the right solver for that problem that you have solved. So the problem, including the model and the properties and constraint, will have certain properties, and when you know these properties, you can select the appropriate solver for it. Then you analyze the solution, and perhaps quite often you need to reconsider the problem you set out to solve first, and then you iterate until you get the solution in the space that you were expecting. And fundamental issues that you should be aware of is that all optimal solutions are extreme points. When you get the solution, it will be an extreme point. Either it will be sitting on the boundary or in a corner of your allowed space, or it will be sitting on a mountaintop. Let's say that you are searching for the highest point in the Nordic countries. Then you would end up in Galdhøpiggen in Jotunheimen in Norway. But that was not really what you wanted, because now we're in Corona and Norway has closed down, so that becomes something that's not allowed. So we have to put in a new constraint, so we only consider Sweden. And then we get Kebnekaise up in Lapland, and that might be fine. Or you might think that your budget for traveling and finding your way all the way up to the peak of Kebnekaise isn't enough. Then you might restrict your search options even more. So this is an example of how you could iterate. Another thing that's important to be aware of is that the optimizer will shamelessly exploit all weaknesses that you have in your model. You as an engineer might think of temperatures or pressures as physical quantities. When you throw it on the optimizer, it's mathematics, and the mathematics disrespect your belief in physics. For example, I have done optimizations over parameters for systems and found that the best solution would be to have a negative temperature in the Kelvin scale, which is completely unphysical. But the optimizer didn't know that it was unphysical because I hadn't told it that I wanted to have a constraint that I needed to have reasonable temperatures. So this is something that often happens, that the solver exploits all weaknesses that you have in your model to find what's best in the mathematical sense. And that's why you often have to reconsider your problem formulation and reiterate. For some problems you have to iterate quite a lot, and also if you work with nonlinear problems, find good initial guesses. For one optimal control problem, when we started to dig deeper into numerical optimal control, it took us about 4 months to get the first convergent solution. We worked a lot on the problem formulation, on getting the things right. And when you have gotten the things right, then it's usually sheer happiness to work with the optimal control and with optimization. This is a bridge from normal optimization to optimal control. In normal optimization we have a finite number of decision variables, while when we come to optimal control we jump up and, for example, we look at the movement of the gas pedal as a control input. And for example, we would like to know how to drive from A to B, say from Linköping to Norrköping, and we want to do that in 45 minutes, and we would like to do it with a minimum fuel consumption. How should we move the gas pedal in a vehicle, for example a hybrid electric vehicle or a purely electric vehicle? The thing that we're wondering then is the curve of u, and this curve of u is an infinite dimensional variable. We're looking at the curve, each individual instant of this trip. We need to know what the control action should be. So this is the essence of control. We're going from finite dimensional calculus to infinite dimensional calculus. And very often we have a cost function, at least in the vehicle side. We want to minimize the fuel, which is an integral. We're minimizing an integral of something. We might also minimize some function at the endpoint that we're interested in keeping at a certain point. For example, we will look at the endpoint in terms of state of charge. When we look at constraints in optimal control, a big constraint is the system dynamics. So here we have the system dynamics. This is the Newton's second law for the vehicle equation. So we have the vehicle motion equation that you should be well aware of now. And then when we have the velocity from the first part, we can insert it into the integral for the distance. And then we have a mass flow, which is a function of the velocity that we're traveling and the control signal that we are utilizing. And we have an initial value, a starting point. We start in Linköping, and then at the final time we need to be in Norrköping, or the point B. Then we also have to respect speed limits. For example, the velocities over our traveled route need to fulfill something that depends on where we are. Initially, when we're inside Linköping, we might have 40 kilometers an hour, then switch up to 60, 70, and then on the highway we're up at 110. And then our control signals that we can utilize are also bounded, so we cannot have infinitely much torque out of the engine if that is our control signal. And this is a difficult problem to solve analytically, and only some special cases can be solved analytically. To solve most of the practical problems we are interested in, we have to go to numerical optimal control. But the theory and the tools, they provide access to some certain elements. And some of the elements that we have is here, for example. This part is the criterion function, the performance index, the thing that we want to optimize. For example, it can be minimize the integral of the fuel flow, so to minimize the total fuel mass, or in an electric vehicle it could be minimize the total energy consumption. Then we could have here an condition that is a penalty on the end state. For example, if you look at a hybrid, the state of charge is usually a state that we want to look at. And for hybrids, we want to make sure that the state of charge is at the desired level. So if we have a pure hybrid, we should have something that's called charge sustaining strategy, as I talked about in the last lecture. And then we're enforcing it to say that the state of charge, to deviate from the state of charge, will cost extra in terms of fuel, because that means that we need to use the combustion engine to generate more electricity. So having a non-optimal state of charge at the end will cost fuel in the future, and this function can then keep track of such things, so you can model these kind of effects. Then we have a system model, which is a core of the constraint. So we have the dynamic equation. X here is a vector valued function now, so we could have many states. And we have the initial condition. We're starting here, and the state at the starting point is this. So this could be like Linköping. Then we have state and control constraints. So the controls must be in their valid region. We cannot gas more than 100% and not less than 0%. And the states needed to fulfill the constraints. For example, if the state of charge is a state in the model, then it needs to be inside its validity region. Optimal control, some historical perspective. It's a really old subject with a rich theory. The old theory comes from calculus of variations. Then we have had much theory, and many methods were developed during the period from the 50s to the 70s, and theory and methods are still being actively developed. There are, on the control conferences, more or less always sessions on optimal control. Dynamic programming was an important breakthrough that was developed by Richard Bellman in the 50s, and we will talk more about his dynamic programming when we look at how to control the hybrid electric vehicle. A modern success story that builds on the theory here in terms of the problem formulations and the numerics is model predictive control. In the predictive step, where you are predicting where you would like to end up and the control signals you need, that relies upon optimal control theory. And now there's a renewed interest for what's called collocation methods, which is a way of numerically transcribing the infinite dimensional problem to a finite dimensional problem that you optimize with computers. There were a few collocation methods during the 90s, but now, since the turn of the millennium, the interest has exploded, and this follows very much from that the computational power of the computers have improved. Just a short commercial break is that there are courses on optimal control, usually at all universities, and at Linköping is this course that I recommend for my students who are interested in this subject area. With that, we have come to another opportunity for taking a break. The main issues in the last two items here was that traditional optimization deals with a finite number of decision variables. It can be many. You can solve problems with 1 million decision variables in some fields. But when you come to optimal control, then the decision variable becomes infinite. So we're searching a continuous curve. The state needs to be continuous, but the control is allowed to switch. But we're still searching after something that is infinite dimensional. And we will look now onto deterministic dynamic programming, and we will do a walkthrough of the tools that you will use when you solve your hand-on assignment. So take a little break and get a little bit recovery before you start the next lecture. Till then, bye bye.